So, let us continue with the two dimensional boundary value problem that we started looking in the last class. And basically let me summarize what we have done in the last class. We started out with the problem statement of general two dimensional boundary value problem, and we also looked at equivalent functional for that problem. This is the problem that we have taken is a second order differential equation defined over a two dimensional domain surrounded by a boundary, and we also looked at how to derive the element shape functions for a 3 node triangular element, and also we looked at how to get the element equations using Galerkin criteria in conjunction with the 3 node element shape functions that we derived, and finally we got element equations. So now let me quickly go through what we have done in the last class. So this is the differential equation, second order differential equation, which is for a two dimensional boundary value problem, and this needs to be solved over arbitrarily defined area A bounded by surface S, and a part of surface on which essential boundary condition is specified is denoted with S1, and part of the boundary on which essential boundary natural boundary conditions are specified is denoted with S2. So these are the two boundary conditions, either of these can be specified, and subjected to these two boundary conditions we need to solve this two dimensional boundary value problem. So that is the problem statement, and using Galerkin criteria we get this equation where n I takes values 1, 2, 3, because there are 3 shape functions for a 3 node triangular element, and using integration by parts, that is Green's theorem, we get these two identities or two formulas. We use these two formulas to simplify the earlier equation. Here nx and y are the direction cosines of the outer normal to the boundary, so using Green's theorem on the first two terms of the equation that we obtained using Galerkin criteria, we get this equation, which can be further simplified by writing equations corresponding to n1, n2, n3, writing all 3 equations together in matrix form, we get this equation. And here the boundary integral over S2 actually gets changed in the second equation as boundary integral over the total boundary S. I gave detailed explanation in the last class. Integral, we can write this because integral over S1 is unknown, and there is no need to evaluate it since corresponding nodal parameters are known. So that is essential boundary condition is specified, and equation containing these terms can be removed from the system before solving for unknown parameters, nodal parameters. Thus, the integral over S1 can be ignored from element equations, integral over S2 can be evaluated using the specified natural boundary conditions. So, that is the reason the first equation can be rewritten as given in the second equation, where the boundary integral over S2 is replaced with integral over the entire boundary. So, now using the specified natural boundary condition, the boundary integral can be simplified further using this natural boundary condition, and when we plug in this boundary integral term into the equations, the complete element equations can be written like this: kx plus ky plus kp plus k alpha times d is equal to r cube plus r beta, or it can be compactly written as kd equal to r, where k is defined as kx plus ky plus kp plus k alpha, and r is defined as r cube plus r beta. And if you see each of these kx, ky, kp, k alpha, they are all area integrals or integrals over the entire domain, and we need to adopt a numerical integration scheme when the integrand becomes complicated. So, this is how kx, ky, kp are defined, and k alpha and r beta corresponds to the natural boundary conditions. K alpha is defined like this, r beta and r q is defined like this. Since k alpha and r beta corresponds to the boundary on which natural boundary condition is specified, it must be kept in mind that k alpha and r beta are added only for those elements for which natural boundary conditions are specified, and if for a particular problem no natural boundary condition is specified, then k alpha and r beta are going to be 0. And please note that each of these surface integrals is going to be a vector having a column vector which is going to be having 3 components, because if there are 3 nodes for the triangular element that we are considering, and that if at each node there is 1 degree of freedom, then these boundary integrals that is k alpha, r beta, r q are going to be having a vector having 3 components, and kx, ky, kp and k alpha are going to be a matrix having dimension 3 by 3, since this corresponds to a triangular element having 3 nodes, and assuming 1 degree of freedom at each node, we get 3 by 3 matrix. So, this k alpha and r beta are added only for those elements for which natural boundary conditions are specified, and equations associated with essential boundary condition must be removed from the global equations before solving. Once we assemble all the element equations, and once we come up with the global equations from the information of element connectivity, and we need to remove the equations associated with essential boundary conditions before we solve the global equations. So, now let us see how each of these matrices and vectors looks like for a 3 node triangular element. and since the shape functions for 3 node triangular element are very simple, since 3 node triangular element is a linear element or linear triangle, it is possible to carry out all the integrations in a closed form, assuming kx, ky, pq are constant over element to get element equations in an explicit form. This is possible only if kx, ky, pq are constant. If they are not constant, the integrand becomes complicated and we need to adopt a numerical integration scheme, which we will be looking at in the later lectures if kx, ky, p and q are not constant. So, now let us assume these are constant, and now let us see how to evaluate, simplify further the matrix kx. Matrix kx is defined like this: integral kx coefficient kx bx times bx transpose integrated over entire element area. And now substituting what is bx, bx is nothing but derivative of shape functions, a vector consisting of derivative of shape functions with respect to x, substituting bx, bx transpose, and you can see, or if you recall, the expressions for shape functions for 3 node triangular element, these n1, n2, n3 are all linear in x and y. So, when you take derivative with respect to x or y, you are going to get a constant vector, a vector which is going to be constant over the entire element. So, bx is going to be a constant consisting of coefficients b1, b2, b3, which are functions of the spatial coordinates of the nodes. So, substituting bx, by, sorry, bx and bx transpose, this integral can be simplified in the form given in the slide, and integral over dA is going to be a. So, this can be further simplified in this manner, and this kind of expressing kx in a closed form is possible only the if the coefficient kx is constant. If it is not constant, the integrand becomes complicated. Similarly, we can write explicit expression for matrix ky, except that we need to substitute by here, which is nothing but a vector consisting of a derivative of shape functions with respect to y, which is nothing but c1, c2, c3, where c1, c2, c3 are functions of spatial coordinates of the nodes. So, substituting all that information and simplifying this integral similar to what we have done, or adopting similar procedure as for the previous case of kx, we get ky in this manner in a closed form. So, now let us look at the other term kp. Kp is defined like this: assuming p to be constant, we can take p out of the integral and multiplying n, which is nothing but a vector consisting of shape functions n1, n2, n3, carrying out multiplication of n and transpose. This can be further simplified in the manner which is shown in the slide. Here please note that this n1 square, n1, n2, n1, n3 and all these quantities are not going to be constant, they are going to be functions of spatial coordinates. So, to carry out these integrations, we need to adopt some kind of numerical integration scheme, or fortunately there is a formula to evaluate this in a closed form. The terms in the Kp matrix are not constant. Fortunately, following simple formula is available for integrating shape functions over a triangular element. So, whatever formula that is going to be given is valid only for integration over triangular region, and this formula looks like this: n1 raised to power alpha, n2 raised to power beta, n3 raised to power gamma integrated over a triangular area is equal to alpha factorial multiplied by beta factorial multiplied by gamma factorial divided by alpha plus beta plus gamma plus 2 factorial, entire thing multiplied with 2a, where a is the area of the triangular region, and these alpha beta gamma are all integrals or integers, where alpha beta gamma are integer powers of shape functions n1 n2 n3. A is area of triangle, and the symbol, this exclamation symbol is denotes factorial operation. So, using this formula we can evaluate each of the components of Kp matrix. Using the integration formula, terms in the Kp matrix can be evaluated here. For 2 terms the details are shown. Integral n1 square over triangular region we can rewrite as n1 power 2, n2 power 0, n2 n3 power 0, because any number raised to power 0 is equal to 1. So, now alpha is equal to 2, beta is equal to 0, gamma is equal to 0. So, with this with this information, substituting this into the formula, we get 2 factorial divided by 4 factorial times 2a, which can be simplified as a over 6, that is one component of Kp matrix, integral n1 square over the triangular region. Similarly, product of n1 n2 integrated over triangular region, it can be written as n1 power 1, n2 power 1, n3 power 0, that means alpha is equal to 1, beta is equal to 1, gamma is equal to 0. Substituting all this information into the formula, we get 1 factorial times 1 factorial divided by 4 factorial times 2a, which can be simplified as a over 12. So, in this manner we can carry out integration of all the components, and Kp matrix can be obtained by plugging in all these integrals. Evaluating other terms in a similar manner, the matrix Kp can be written like this. And again, once again, this is this formula, application of this formula is possible only if we are integrating the shape functions over triangular region, and p is constant. Here p is assumed to be constant. If p is not constant, the integrand becomes complicated and we need to adopt numerical integration scheme. So, we have seen how to evaluate kx, ky and kp for a 3 node triangular element. Now, let us look at the other quantities. Rq is defined like this: integral or q times n integrated over triangular region, and here also if q is constant we can take q out of the integral, and rest of the for evaluating rest of the quantity, that is integral of any shape function n1 n2 n3, we can adopt the formula that we have seen earlier. The formula that we have seen is n1 power alpha times n2 power beta, n3 power gamma integrated or triangular region is alpha factorial times beta factorial times gamma factorial divided by alpha plus beta plus gamma plus 2 factorial times entire thing multiplied by 2a. So, this formula can be applied to simplify each of the component of Rq. Example, integral n1 over triangular region can be written as n power n1 power 1, n2 power 0, n3 power 0, and which can be simplified to 1 factorial divided by 3 factorial times 2a, and which is equal to a over 3. Similarly, evaluating other components, that is integral n2 over triangular region and integral n3 over triangular region, we get all the components of RQ, and RQ can be written like this. And here once again Q is constant, then only this is valid, and this is how we can evaluate area integrals, and we are left with 2 more integrals which are boundary integrals k alpha and r beta, and that these integrals we need to evaluate along the element edges. Since boundary integrals, or since the boundary of element consists of 3 straight lines like this is the triangular element that we are looking at, or we are trying to develop element equations for this kind of triangular element. Since the boundary of element consists of 3 straight lines, integrals k alpha and r beta must be evaluated separately for each side of triangle. So, we need to evaluate these integrals for each of the sides 1 2, 2 3, 3 1 separately, and if you see the schematic there, for each of these edges local coordinate system is defined. S for side 1 2 starting at node 1, S is equal to 0 corresponds to node 1, and S is equal to length of side 1 2 corresponds to node 2. Similarly, for side 2 3 local coordinate system is defined, and side 3 1 local coordinate system is defined. So, now we need to evaluate these integrals for each of these sides, taken each of them separately. So, now the details for one of these sides will be illustrated here, and one more thing to note is along side 1 2 the shape function of node 3 is going to be 0, along side 2 3 shape function of node 1 is going to be 0, along side 3 1 shape function of node 2 is going to be 0. So, integral along side 1 2 to evaluate it, we require what is the length of side 1 2. Side 1 2 can be calculated once we know the coordinates of each of the nodes. With the information of coordinates of node 1 and node 2, we can calculate length of side 1 2. Then integral k alpha along side 1 2 becomes this integral evaluated along side 1 2 alpha, the value of alpha is going to come from natural boundary condition alpha times n1 n2 n3 vector and n1 n2 n3 vector, and we are going to get a 3 by 3 matrix here, and we need to evaluate this integral over side 1 2. So, we can adopt numerical integration scheme, because we cannot use the formula that we have seen earlier, because that is only applicable for integration over triangular region, that is for area integral. So, now along side 1 2 shape function of node 3 is going to be 0, while n1 and n2 are linear functions of S. How to get the shape functions of n1 n2 alongside 1 2, we can use Lagrange interpolation formula that we already learned for one dimensional. When we are looking at one dimensional elements, we already looked at Lagrange interpolation formula for 2 node linear element. We can use that. Using the one dimensional Lagrange interpolation formula, the trial solution alongside 1 2 can be written like this: n1 times t1, t1 is the field variable value at node 1, n2 times t2, t2 is field variable value at node 2, and the shape function of n1 can be obtained using Lagrange interpolation formula, taken side 1 2 alone. Shape function of node 1 alongside 1 2 is given by L12, where L12 is length of side 1 2 minus S divided by length of side 1 2, that is shape function of node 1 alongside 1 2. Shape function of node 2 alongside 1 2 is given by S divided by length of side 1 2. So, these formulas can easily be obtained using Lagrange interpolation formula. So, since shape function of node 3 is 0 along side 1 2, we can rewrite this equation as n1 n2 0 times t1 t2 3 t3 as given in the equation there. So, this is how trial solution can be written in terms of nodal values t1 t2 t3 alongside 1 2. So, substituting this t value, substituting the shape function values of n1 n2 n3 alongside 1 2 into k alpha, we get this one. Carrying out the vector multiplications, we are going to get this matrix, and still this needs to be evaluated over side 1 2, that is s small s going from 0 to length of side 1 2. We can adopt numerical integration scheme if the integrand is complicated, or if integrand is simple, we can evaluate this in a closed form. Since here integrand is simple, we can evaluate it in a closed form by integrating each of these components with respect to s and substituting the limits of integration 0 and L12, we get the closed form solution of this k alpha, assuming alpha to be constant, and this formula or this equation is valid only when alpha is constant, assumed to be constant. If alpha is not constant, then we need to integrate keeping alpha inside the integral. So, this is how k alpha can be evaluated. Similarly, r beta is defined like this. Again we need to evaluate r beta separately along each of the sides 1 2 2 3 and 3 1, and here evaluation of r beta alongside 1 2 is illustrated. Substituting n, which comprises of component of shape functions or shape function value n1 n2 n3, put in a vector form, substituting that r beta can be written as beta times a vector consisting of n1 n2 n3 integrated over side 1 2, and that can be rewritten by substituting the shape function of n1 n2 n3. Since n3 is 0, we can simplify this further, and assuming beta to be constant, we can pull beta out of the integral and we can get the closed form solution of these integrals, and r beta is given by the value which is given in the slide, that is beta times length of side 1 2 divided by 2 multiplied by a vector consisting of 1 1 and 0. So, similar operations can be repeated if required for side 2 3 and 3 1. When I say if required, I mean if natural boundary conditions are specified alongside 2 3 and 3 1. If natural boundary condition is not specified along 2 3, or if natural boundary condition is not specified along any of these sides, along that side we do not need to evaluate these integrals. So, for side 2 3 and 3 1, integrals can be evaluated in a similar manner, except that local coordinate system should be defined as shown in the schematic, and noting that the shape function of node which is not part of a side is going to be 0 along that side. In fact, the only thing different from other sides is the placement of zeros in the above matrices. So, that is what I mentioned. So, carefully noting which node is not part of the edge, the shape function of that node is going to be 0 along that edge, and taking care of that we can get the integrals for side 2 3 and 3 1. So, now to see application of this, whatever we have developed element equations, we will take up an example, numerical example. And also it is easy to verify that for sides 2 3 and 3 1, the simplified form of k alpha and r beta are this. So, now let us take a numerical example. Say, so a numerical example is going to be presented here to illustrate how to use the above element equations and to illustrate the assembly process for 2-dimensional problems. So, now let us take the problem statement: using 4 triangular elements find an approximate solution of following boundary value problem. This is the boundary value problem or the differential equation for which we need to find solution. The field variable is t, and this differential equation is valid over domain A, where A consists of 4 triangular elements, 4 3 node triangular elements. All the nodes are numbered 1 2 3 4 and 5. Fifth node is at the center of A, and along each of the edges the boundary conditions are also shown, and also the geometrical details are given, the problem dimensions, and from the details that are geometrical details that are given in the schematic, we can easily using the coordinate system that is defined, we can easily figure out what are the nodal coordinates of each of the nodes 1 2 3 4 5, and also elements are numbered as 1 2 3 and 4. Essential boundary condition is imposed. Looking at the boundary condition, we can easily figure out which is essential boundary condition, which is natural boundary condition. Essential boundary condition is imposed on side 3 4 along the edge which is connecting nodes 3 and 4, and natural boundary conditions are specified along edges 1 2 2 3 and 4 1 along the remaining 3 edge sides. So, now we have all the information like boundary conditions are given along all the edges. So, we can easily identify what is alpha and beta when we compare this with the general 2 dimensional boundary value problem, and also given the differential equation we can also find what is kx, ky, pq if we compare with the general 2 dimensional boundary value problem. So, now let us start assembling the element equations starting with element 1. Element 1, first we need to identify what are the nodes, identifying element connectivity as 1, 2, 5. So, this is how element 1 connectivity is identified 1, 2, 5. So, local node 1 is same as global node 1, local node 2 is same as global node 2, local node 3 is global node 5. So, identifying element connectivity as 1, 2, 5, we have element sides, side 1, 2, local side 1, 2 is same as global side 1, 2, local side 2, 3 is going to be side 2, 5, and side 3, 1 is going to be local side 3, 1 is going to be 5, 1. So, with this understanding and also identifying from the given differential equation what are the coefficients kx, ky, pq, comparing with general 2 dimensional boundary value problem, we can easily identify kx, ky as 1, p is equal to 0, q is equal to 30, and alongside 1, 2, if you see this element 1, only alongside 1, 2 natural boundary condition is specified, and side 2, 5 and 5, 1 no natural boundary condition is specified. So, alongside 1, 2 the given natural boundary condition, compare that with the boundary condition for general 2 dimensional boundary value problem, and identify what is alpha and beta. Alpha is 3 and beta is 15, it can be easily verified. So, we have all the information. So, now our job is to plug in all these quantities into the element equations that we developed for a 3 node triangular element, and nodes are the element connectivity is like this, nodes 1, 2, 5. So, noting down the coordinates of these nodes from the geometrical details that are given in the problem, x coordinates and y coordinates of nodes 1, 2, 5, and with this information is required because we need to calculate the shape functions, for which we need to calculate f1, f2, f3, b1, b2, b3, c1, c2, c3, which are all functions of spatial coordinates. So, we can calculate f1, b1, c1, similarly f2, b2, c2, f3, b3, c3, and finally we can calculate the shape function expressions using these coefficients f's, b's and c's, and also we require what is the area of triangle A and what is the length of side 1, 2. All that information can also be computed once we know down these nodal coordinates. So, with this information we can easily find the shape function expressions n1, n2, n3 corresponding to the element 1 connecting nodes 1 to 5. So, substituting these values into equations derived in the previous section, that is for we already derived element equations for 3 node triangular element, substituting the B's values B1, B2, B3 into Kx matrix that we already have, and C1, C2, C3 values into Ky matrix that we have. We get these two matrices Kx and Ky corresponding to element 1, and also K alpha identifying what is alpha, and plugging it into the element equation that for K alpha that we already developed, we get this K alpha for side 1 2. And since P is 0, coefficient P is 0, Kp is going to be 0, 0 in the sense it is going to be a 3 by 3 matrix of zeros, and also Rq and R beta can be assembled like this. Rq is going to be 10 10 10, a vector consisting of 3 components each of which is equal to 10, and R beta is a vector consisting of minus 15 15 0. So, this is for element 1, these are the quantities for element 1. So, using all these quantities, complete equations for element 1 can be written like this, where T1, T2, T3, where T1, T2, T3 are the local nodal parameters for element 1. That is why it is written as T1, T2, T3 superscript 1, that means it corresponds to element 1. So, similar operation we can also repeat for other elements, element 2, element 3 and element 4, except that we need to keep a note carefully on the element connectivity and also the coordinate of elements, coordinates of nodes. So, for element 2 the details of workout is shown here. Element 2 the connectivity is defined like this, 1 5 4, that means local node 1 is same as global node 1, local node 2 is global node 5, local node 3 is global node 4. So, with this understanding and also comparing the given differential equation with general boundary value problem equation, we get this Kx Ky Pq, which is similar to element 1, and natural boundary condition. If you see the natural boundary condition that is specified along side 4 1, that is the local side 3 1, we get this information alpha is equal to 0, beta is equal to 0. So, for this particular element K alpha is going to be 0 and K beta is also going R beta is also going to be 0. So, once we have all that information, following the procedure similar to that for element 1, we get Kx, Ky and Rq, and rest of the quantities Kp, K alpha, R beta are 0. So, using all this information we get the complete equations for element 2. Like this. Similar operation can be repeated for element 3, noting down local node 1 is same as global node 4, local node 2 is global node 5, local node 3 is global node 3, and noting down Kx, Ky, Pq, we get Kx, Ky Rq, and there is along this along any of these sides of this element natural boundary condition is not specified. So, K alpha, R beta are going to be 0, P is 0, that is why Kp is equal to 0. So, complete equations for element 3 are given by this. Please note that for element 3, even though along edge 3 4 essential boundary condition is specified, at this stage we have not used that information, but later when we assemble the global equations based on the element equations for all the 4 elements, and once we get the global equation, at that stage before we solve the global equation system, we impose this information, that is along side 3 4 t value is 100, at that stage we are going to impose. So, now let us go to element 4, identifying local node 1 as global node 2, local node 2 as global node 3, local node 3 as global node 5, and rest of the information similar to the other 3 elements. We can get kx, ky, rq, and rest of the matrices and vectors are going to be 0, because p is 0 and alpha is 0, beta is 0. Complete element equations for element 4 are these. So, now we have element equations for element 1, 2, 3, 4. So, now we need to assemble the global equations. For that we require global location coefficients in the element matrices. So, we look at, once again we look at the element connectivity or the nodal connectivity for each of the element. For element 1, the nodal connectivity is like this 1 2 5, and for element 2 1 5 4 is the nodal connectivity. So, with this information we can easily identify at what locations the contribution of each of the elements 1 2 goes into the global equation. So, element 1 contribution goes into the locations that are given under element 1, and element 2 contribution goes into the locations that are given under element 2 into the global equations from the local equations. Similarly, for element 3 and element 4, element 3 the nodal connectivity is 4 5 3, and element 4 nodal connectivity is 2 3 5. So, we get this global locations for coefficients in element matrices. So, using this information we can easily assemble the global equations by plugging in the corresponding locations the local element equations contributions into the global equations, plugging in based on the information that we just have, we get these global equations. So, at this stage we need to impose, before we proceed further, we need to impose that t value along a side 3 4 is 100, that is t 3 is going to be 100, t 4 is going to be 100. We need to impose that condition. That condition we are getting from the problem that is given to us. Essential boundary condition is t 3 is equal to 100, t 4 is equal to 100. Corresponding terms in the right hand side vector are unknown. So, whenever essential boundary condition is specified in the global equation system, the corresponding terms in the right hand side vector becomes unknown, that we already have seen. We have seen that kind of thing earlier when we are solving the previous problems. So, final equations after imposing T3 is equal to 100, T4 is equal to 100 becomes this, and this to solve for the 3 unknowns T1, T2 and T5, we need to rearrange this equation system. The 3 unknown T1, T2 and T5 can be obtained from equations 1, 2 and 5, and the previous global equation to solve for T1, T2 and T5 needs to be rearranged like this, and which can be simplified and solved for T1, T2 and T5. Entries in the third and fourth column multiply the known values and can be moved to the right hand side. So, entries in the third and fourth column multiply by the known values, that is 100 and 100 can be moved to the right hand side, and the previous equation can be rearranged like this to solve for T1, T2 and T5. So, once this equation system is solved, we get solution T1, T2, T5 like this. So, once we obtain solution for T1, T2 and T5, we can go to each element and do post processing. Complete solution and its derivative in each of the element can be obtained, over each element can be obtained from the shape functions. So, shape functions corresponding to element 1 n1, n2 and n3. So, t is given by t at any point in the element is given by n1 times T1 plus n2 times T2 plus n3 times T3. So, for element 1 we know what are the nodes. For element 1 the nodes are 1, 2, 5. So, using the nodal values T1, T2 and T5, we can get T value in over element 1 using this, which can be further simplified. And once we have this, we can easily calculate derivative of t with respect to x, derivative of t with respect to y, and this gives us information about derivative of t over element 1, and similar operation can be repeated for other elements. Similarly, for other elements we get t is equal to this, for over element 2, over element 3 t is this, and over element 4 t is this. And also we can check whether the solution for T1, T2 and T5 that we obtained is how accurate is that by plugging in into the natural boundary condition alongside 1, 2. Check for natural boundary condition alongside 1, 2. So, this is the natural boundary condition that is given alongside 1, 2, and partial derivative of t with respect to n is defined as partial derivative of t with respect to x times direction cosine component nx plus partial derivative of t with respect to y times direction cosine component ny. So, we can write the given natural boundary condition like this, and for side 1, 2 nx is equal to 0, ny is equal to -1, substituting that we get this. And now plugging in t value, we can, and derivative of t value, we can see that the equation is not satisfied exactly. So, we can conclude that solution is not very good, and this is expected since we used only 4 linear elements. 4, please note that 3 node triangular element is a linear element for 2 dimensional problems. So, we used 4 linear elements, which may not be good enough to get the accurate solution for this problem. So, to get more accurate solution we need to use much finer refinement for this problem. Okay. So, with this we will continue in the next class.